What we're looking at here is the organic chemist's periodic table. And so a couple things to note about this table. It's a condensed table, so it doesn't have all the atoms that the full periodic table does. And that's because we don't use all the atoms in organic chemistry. These are actually the most common atoms used in this course. And so another thing to note is that the noble gases, this is review from Gen Chem, noble gases have a very stable electron configuration. And so this is important because it is actually going to be the goal of all the other atoms to gain the stability of those noble gases. So if we look at helium, helium only needs one additional electron to get to hydrogen only needs one additional electron to get to helium's What we're looking at is the organic chemist's periodic table. And a couple things to note about this table is that it's in a condensed table, and so it doesn't have all the atoms that the full periodic table does. If we look at the noble gases, and this is review from Gen Chem, we know that the noble gases have a very stable electron configuration. And so a lot of the other atoms are going to have that goal to attain that same stable configuration. So if we look at hydrogen, for example, hydrogen only needs one electron to get to helium's electron configuration, and therefore that stability, whereas carbon needs 4 additional electrons to get to neon's electron configuration and that stability. And so when we look at atoms and we look at their goal, what we're going to see is hydrogen's goal is a duet. That's 2 electrons is what it needs to achieve that noble gas electron configuration. And so when we look at the row 2 nonmetals, their goal is to gain electrons to get to neon's electron configuration. So carbon, like we said earlier, needs 4 additional electrons. Oxygen, as an example, will need 2 additional electrons to get to an octet, which again is that stable electron configuration, and it does so by gaining electrons. And this is a distinction from row 2 metals, like lithium, for instance. Lithium loses an electron to get to a duet, and therefore that stable electron configuration. Now, row 3 atoms are going to be the exceptions to the octet rule. And the reason that is, and we'll talk about here in a second, so we're going to say so they're the exceptions to the octet rule. They may or may not follow the octet rule. Now, the reason that is because row 1 atom, so hydrogen, as an example, has 1s subshell. Row 2 atoms have 3p subshells. So this is row 2, that's row 1. And then when we get to row 3, what we have is 5d subshells. And so what that means is because there are these additional 5d subshells, atoms in row 3 and beyond can actually take more and have more than an octet because they have these 5 empty D subshells. So row 2, if we look at it, there are 2 electrons in each P subshell for a total of 6. And then we have the 2 electrons in the 1s subshell. There's 2 of them, and so that's 2 here plus the 6 here. That gives us that octet, the total of 8, that octet. Whereas when we get to 3 and beyond, we can actually violate that octet by taking in more electrons. And so to recap, what we have is a condensed periodic table because we don't use all of the atoms in organic chemistry. We note that the noble gases have a very stable electron configuration. We know hydrogen has a goal of a duet, adding an electron to achieve that noble gas configuration that's very stable. Row 2 want an octet for the nonmetals, and then for the metals, they can actually lose 1 or 2 electrons to get to the helium and have a duet, and therefore the stable electron configuration. Anything row 3 and beyond can violate the octet rule because it has these 5D subshells.